Hello, good afternoon. Okay, let's start our class today. First, I'd like to open our high CLT, which was distributed to all of you. Well, I often introduce this tool for you, and I'm sure if you have any problems with using these tools, please let us know through cutoff. Last time, what we have discussed was about how to generate failure envelope using these tools. Let's continue from that point. And this slide also was distributed to all of you. And this slide was not so much clear.
교수님 혹시 화면 공유해 주실
예,
수 있습니까?
okay, sorry.
네, 감사합니다.
Okay, this is the PowerPoint which I distribute, and this is the high CLT which I also distribute to you. Now, last class we were discussing about how to generate a failure envelope, which can be very important issue in designing of composites. Well, there is not much theory involved to generate a failure envelope, but by using the feature of the quick chart, we can automatically draw a failure envelope, which can be very useful in design of composite or understanding the behavior of laminate. Basically, what we can do is that we like to draw this, let's say, only for the N1 and 2, say this laminate, whatever laminate we have a N1 and N2, and we like to understand which load combination will reach the failure. For example, let's say we have a N1 and N2, and this is a domain. We like to draw failure envelope. So how to draw the failure envelope? That's the point. Let's say to draw any point. Let's say this point, this much N1 and this much N2. This material, the composite will fail. So how can we find this point? This point is indicated by the theta. Theta gives us the ratio between the N1 and N2. So how to find this point automatically, rather than just keep applying this load. It would take a long time to find that point. Now, how can we find that point automatically? Well, the basic, the key point is that all the theory we are covering right now is a linear. So we start with a unit circle, just a unit circle, meaning that with the radius of r. This is just a fictitious circle. And then this magnitude will be just the unit radius r, the radius equal 1. Then we apply this much load, and then we get the SIO failure index, which give us the safety factor. So once we find that point, and then we find the safety factor, we can find this point by the ratio of the safety factor. So this is the one point we can find. So to find that point, it just takes one time of calculation. Again, we apply this much load, and then we found the safety factor. We increase them that much. That will give us the failure point. And for the given theta, now we do the same thing. We have a different ratio theta, and then we find the safety factor, and then we increase that much the point by increasing radius by the factor of the safety factor, and then do this. So we iterate, we do this at that point and that point, and we keep doing so and generate the full failure envelope. Again, this is very useful. So I just mentioned N1, but more precisely, we can say the sigma 1. Let's divide by the thickness. N1 divided by the thickness will give us a stress. And then safety factor is the, I just mentioned here, psi u failure index. So divide by the psi u will give us this much point. So that is the sigma 1 failure and the sigma 2 failure, okay? So this is the very simple approach, but again, very powerful procedures we can understand. And this is helping us to draw the failure envelope and also helping us to understand what it means by the failure envelope. So let's do it again. Here, N1 and N2, as we just discussed, we just give a cosine. Here, I just mentioned that N1, okay, N1 is just a cosine theta and sine theta to make the unit circle for the given theta. So cosine and sine theta. So what we're gonna do is that we change the theta from 0 to 160 degree. That's the one we like to do. So cosine theta and sine theta, that's why we have here the cosine theta and sine theta, and input will be a variables, and the input is the angle. So we just input is the degree and changing into a radian. And N2 will have a sign. So this input is again, input is the one variable. We're gonna change that. So this is the, as you can see, this is input. Okay. Well, basically, that's all we need to do. The psi u failure index is the one. This is the one we calculated. Just the make sure where this comes from. This comes from the here. This is the failure index of the psi u. Which is the as you can see, a maximum. Okay, maximum of the bottom and top. Each ply will have a top and bottom stress ratio. And this one, as you can see here, we get all the values. Each ply will calculate it psi u failure safety factor or failure index based on the psi u. So this is the older formula. You can understand that. Okay, so and to draw the circles, simply I just had a sample quick chart input and output, because you will need this quick chart for many different purposes. So I just have a sample here. So for your convenience, so if you want to have a plot failure envelope, you just copy, and as you can see, N1 divided by total thickness and the psi u failure index. So all you need to do is just just copy and paste, and then you can just delete that. And that's it. That's all you need to do. Again, this input is a variable, and as you can see, this goes to the other important point. It goes to here, and then goes to there. This load will be used to calculate all the failure index and safety factor. So finally get this one, and that. Finally, we get the safety factor. So which we already covered in the our lecture note. So anyhow, F psi u is the one here, okay, which was calculated as the output of this laminate and load conditions. Okay, so next step is that this is the one you can enter, change the worksheet you like to have as an output. So let's say this is the you can say failure envelope 1. So all you need to do is just click here, and then angle will be 0 to 360. Or you can start with one angle, and then step value can be 1 degree or 2 degree. Is up to you. So this macro, what it does is very simple. You just repeat the same calculations. So this is the input versus sigma 1 and 2. And to draw the failure envelope, what you need to do is that you just select this much, and then draw. This is the one we like to have. And to show, to understand, to better understand this failure envelope, is always recommended that x-axis this much scale, and then the y-axis scale better to be same scale, so that we can graphically understand what the failure envelope looks like. Okay, so as you can see, I'm gonna just copy and put it into here. Okay, well, I'm gonna we didn't emphasize enough about the laminate sequence, but as you can see, we use the quasi-isotropic, and each ply thickness is 0.125, so it's precisely quasi-isotropic. And then material property number 4, that is the T700. So I'm gonna just copy here. So this is the case, and this is a simply output. Okay, very simple, but the output giving us a lot of helping us to understand that. First of all, since this is a quasi-isotropic, and N1 and N2, and this will be a pretty much symmetric with respect to this axis. In other words, this is the laminate like this. I'm gonna draw from here. So this is a 0 and 90 and plus 45, and minus 45 and symmetric. So this one, what does this point, what does it mean? It means that we have only x-axis load. The strength will be, what is that? 500. So about 250 megapascal. Okay, that is the strength. And now, what is this point? This point means that we only have this load, right? This load, and we have here is about the 250 megapascal. I'm sure that this strength and that strength should be the same because this is a quasi-isotropic. And so that's the one thing we like to check. And another point is that this point, that point, what is that? What that point? That is the point we just the same load, but with a compression. So let's say we compressed this way. What will be the strength? Well, this is a y-axis, and the compressive is here. So as you can see, we can observe that this one and that, oh, this is the higher than this, about twice, 500 megapascal is the compressive strength. Please turn off your mic. And now the in x-axis compressive like this, we have that point, right? This is x-axis compressive. Of course, that point and that point is the magnitude should be the same. So we got this anchor point, right? Now, very interestingly, what would be the strength here? What would be the strength here? Why the strength is so high in compressive zone? What does it mean? When we apply the compressive like that, this is a N1 and N2. This happen to be same, but the compressive. This line means that N1 and N2 is the same. So if we compress in the same way, but the compressive way, this strength will be really, really high strength. Why? Because it's associated with compressive. That's the one point. And also, this is the x and y direction in the same load, so that it prevents the simple failure on the uniaxial load. So it's good to know, good to understand that if we apply the load together like this, then the strength will be really high, like this much. So that is the about 1750 megapascal. That's the about the numbers. So as you can see, compared to this, we have a lot of high strengths. And another observation will be this point. What is this point? That point is the even higher than now the I'm gonna delete this load. Now we apply the tension, but the same magnitude in 1 and 2 direction. So as you can see here, if we here, I'm gonna delete this point. And as you can see, here and there is a slightly increase that, right? Slightly increase that. So that is the point. So here was the about the 250, but now here it will be about the 300 megapascal. So this is also important to understand that if we apply the tension load in the same direction, the strength will increase as well. Okay. Now we have another important load ratio. For example, if we have a pressure vessel is a very important, very practical case. this is the N2 and N1. N1 is the always, this is a 2 times of N1. So N2 and N1 is a 2-to-1 ratio. What does it mean? 2-to-1 ratio. 2-to-1 ratio means that we have this is a 2-to-1 ratio. So that is the line. That is the line. I would say N2 equal 2 times of N1. So this is the line. So since it's a tension, that is the strength. That is the strength when we make the quasi-isotropic. So this is the strength. As you can see, is a little bit higher than uniaxial strength. So it's good to understand where we are, the point in the failure envelope. Okay, so now let's do the exactly same, but let's say a little bit different. Okay, different layup sequence. Last time we observed that this for the high pressure vessel case, the when we consider this kind of biaxial like this, say this is angle, and this will theta about 54 degree or 55 degree. 54 degree was giving us the best. So if we draw the load, this is N1 and N2. So N2, this biaxial 54 is always giving us the highest strength compared to these types of the quasi-isotrope. Let's try to observe that one from here. So here, rather than 0, and we just mentioned minus 54 and plus 54 and 54. Okay, well, minus 54, sorry, 54 and 50, just plus 54. So as you can see, plus, minus, and then symmetric. Okay, let's say we chose this laminate rather than 0, 90, plus minus 45. Of course, there are same number of 8 plies, and then we let's try to draw failure envelope and see how the failure envelope looks like. Okay, so let's try to have this one. Say this is the envelope 2, and then that's all you need to do actually. Nothing else. We just change the layup sequence, and then let's try to draw the failure envelope. So from 1 to 360, and then plot them. And then here, and plot. Okay, plot here. Okay, so let's try to, it's always good to have a same ratio. Same ratio means that, you know, this is the, what's the value about the, well, I'm gonna change this guy into scientific. Okay, so this is the 50. Okay, sorry, 500 megapascal. This is a 500 megapascal. So I like to have a same ratio like this. Okay, like that, like that. So this length, okay, slightly more. I'm just trying to make this is a scale so that this is the same ratio. Okay, like this. Now, as you can see that, I'm gonna copy this one into here and then try to plot side by side. As you can see that, well, this failure envelope is the, as you can see, this is, you can observe that this is very high, higher than this uniaxial strength. And why this is a high? Cannot plot it precisely, but as you can see, this is a tension mode. And here, I'm sure this will be the 1:2 ratio. See, this plot, we chose the biaxial 54-degree, and this angle is well known that this is giving us the best for the pressure vessel. Pressure vessel is the again 1:2 ratio. So as you can see, Y biaxial 54. 54 again is the plus minus 54 symmetric. No, we had one more, right? To make the same 54 and symmetry, 8 plies. And then again, this is the about the same ratio. I mean, 1:2 ratio, giving us the highest strength. That's why biaxial 54 is the always the highest strength for the pressure vessel. Or graphically, you can just plot, copy here. I'm gonna get rid of this. Where the other one? We can copy this, and then we simply overplot here. As you can see that now you can compare with the quasi-isotropic with the biaxial, and as you can see, even this pressure vessel again is the load ratio is always this way, right? Along always this line. So this the same number of ply, but the biaxial 54-degree giving us always the highest highest strength. Now you can understand that why this can be higher than others is very important. Now you may wonder why 54-degree is so important. Well, this is the you can say that you know, in composite we have a 54-degree like that, and then always the way we design is that the fiber has to support most of the load or all the load. So we starting from backward. Backward means that, let's say the fiber take over all the load. This is the fiber, and this is the I would say sigma 0, and this is the another sigma 0, and this is the angle. And let's say there is no load, but the fiber and the load in the fiber, this is the load, the carries, fiber carries all the load. Now, the let's say this is a sigma 1 and sigma 2. I'm sorry, I used the sigma, okay, yeah, sigma 1 and sigma 2. So sigma 1 And by the stress transformation, sigma 0 times cosine, this is a scalar because this is a second order tensor. And sigma 2 is the sigma 0 and sine scalar. Okay, it's a little bit maybe new to you, but again, we have a stress sigma 0. We assume all the fiber, only fiber support the load. That is the sigma 0. Now, with that stress, we transform this stress into a one direction into a two direction. So this is the stress transformations. Okay, so this is a stress transformation. And now what we know is the sigma 1 ratio, sigma 1 versus sigma 2 is that this is a 1:2 ratio. We know that this is a pressure vessel loading case. So simply we divide by this over that, sigma 1 divided by sigma 2, and sigma 0 will disappear. And then cosine scale theta and sine scale. Okay, so this is a help. Or inversely, I'm gonna write down here. Tangent scale theta will be what? 2, right? This is the best optimal theta which can support the pressure vessel load by the fiber only. So this will be the ideal case. Then what is the theta here? This is very simple equations. Then this is the what? Arc tangent, and number is a 2. No, is a the yes, it was a 2. Okay, I'm gonna show that equation. This is a tangent scale. Oh, sorry, root 2. So this is the square root. What's the angle? Well, this is the angle. We convert into a degree. Then as you can see, 54 degree. Okay, so 54 degree or 54.7 is nothing but tangent theta is simply ratio 2. Okay, this is the we should remember that this 2 comes from 2:2 ratio. Again, I'd like to remind you that N1 is the PRT and N2 equal PRT. So there will be a 2:2 ratio. That's why a 2 here, and then a scale is coming from here, stress transformation. So theta is simply 54 degree. Okay, this is a pretty much universal value, and this is a very well-known angle, and it's good to understand that. And now from failure envelope, why 54 degree is important? This is the as you can see, this is the biaxial 54, and then you can see this giving us the highest failure envelope. Okay. Now another things you can think of is that, okay, so far we plot the the sigma 1 and sigma 2 is a failure envelope. But how about the sigma 6? We can always have a laminate and sigma 1 and sigma 2 and sigma 6, right? That is the 3 component sigma 6. How can we consider sigma 6 in this envelope? So this one was the sigma 6 equals 0. Now imagine that we have a, say this is a sigma 1 and sigma 2 and sigma 6. And then the one we plot was the just the on this plane, right? Sigma 6 equals 0. And then if sigma 6 is a non-zero, then we will have a sort of this kind of a 3D ellipse or some the volumes. So that would be the one. How can we generate that one? So we can apply simply sigma 6 will be a certain value, and then we can plot again and plot again. So sigma 6 will be another non-zero value, okay? And then we can reduce that. So let's try that one. So let's get back to quasi-isotropic. So quasi-isotropic will be 0, 90, minus 45, and 45, and that is a symmetric. Now, when we apply this much load, you can apply certain load here, okay? Certain load here, say you can have a non-zero value here, okay? You can have a non-zero value here, and then you can plot that. So I'll say sigma 3, sigma 6 failure, which cannot be plotted in 2D, but this can be a very similar concept. Just copy and paste here. Instead of N2, we just have a N6, something like that, okay? So right now we consider only a 0 value. Then this is the one we consider that, and then this one you can have a say start with a 0.5, 0.5, and remember this one is a radius is 1. Now we have a 0.5. Then you can imagine that we have a 0.5 plane, and then we can have another plot, okay? So we can say this is the 1-1. So now, of course, the sigma 6 is a non-zero value, and we can simply plot here like that, and then we can plot, and this one and compare with this failure envelope 1. That was the no shear stress. Now you have a compare that. You can see that if this shear stress is existing, the failure will envelope will change it this way, and you can keep trying that, right? You can keep trying that, or you can plot sigma 2 versus sigma 6 with the non-zero stresses, and you can also simply plot sigma 2 versus sigma 6. It is not easy to visualize, but I just want to give you an idea about the effect of the shear stress on the failure envelope. Okay, that can be one interesting result. Okay, so as you can see, you can do a lot of study using these features. Okay, now another important point in pressure vessel is that, okay, in the pressure vessel, we have chapters on pressure vessels, and here, okay, I just want to make one comment that again, this pressure load and N1 and N2 is always a 1:2 ratio, right? And we can plot this way and so on. What I like to emphasize is that what will be what if this laminate, this can be any laminate sequence, right? What if this is unsymmetric? Well, but in the pressure vessel, curvature has to be 0. Curvature 1 and curvature 2 and curvature 6 will be 0, which means that any layup, whatever layup sequence under internal load, that would not cause any curved bending. So this is the condition. In other words, we have a N1, N2, N6, and moment to 1 and moment to 2 and moment to 6. And then we have A, B, D matrix with epsilon 1, 2, and 6, and curvature 1 and curvature 2 and curvature 6. So in reality, precisely speaking, we are applying this load, and also because of this cylindrical geometry, we don't know exactly what the momentum should be, but we do know this curvature should be 0. So in this 6x6 equation, what we know is that this value will be given like this, and this should be a 0. Okay. So whatever layup, the B matrix may not be 0, okay, may not be 0, but in doing so, when we calculate all the stresses, we have to specify this is the given and this is a given, and we can calculate this term and that terms. And that is the one we need to understand that. That's why you can see here the load option. Load option can be this is a little bit advanced topic. Load can be this one, and that is can be given, and then this can be output. And another combination will be this can be given and others can be obtained. Or we can apply this one and then others can be obtained. And there can be some combination. Again, this load can be all generally given, but the pressure vessel, since this is a cylinder, we are given this one and this curvature rather than moment. So to perform that one, that's why we have a choice here that if one, then no impermanent load and moment will be given, and 2 is a moment, no impermanent load and curvatures are given, and then and strain and curvature. And then 4, there will be a 4 is for the pressure vessel. So to have that one, you just enter the 4 here. Then you can see that here will be here. This is the one, load one, load option 1, 2, 3, and this is a 4. If this is a 4, then curvature is a 0, then other strain will be calculated, and then stress will be calculated. So here we already have some, well, that is the, by the way, that is the same as the case 2. Case 2 is a load and curvature. So case 2 is the, as you can see, pressure. This is a pressure case, very typical. So PR over 2 and or PR and others is 0. So just for the convenience, you can just choose 2 or choose 4, and you can apply the pressure. And for example, 700 bar times 2.25, giving us the 1.75. And radius is the cylindrical cylinder radius of the pressure vessel. Then and the layup sequence. Then simply that gives us the all the stress analysis. Okay, so again, this tool can be very usefully used to calculate the stress distribution inside the pressure vessel for any layup sequence, any ply thickness and any layup sequence. You simply choose the two, and then you get all the stress distributions. For example, okay, let's just try to this and 2, and then a pressure. This is a hydraulic. Okay, this is a 700 bar, 70 megapascal, 2.25 safety factor, and the radius is a 300. I mean, the diameter will be a 310. It's a typical diameter or radius, and then this pressure is automatically applied. And now each one will have this much layup sequence and things like that. And so let's say now giving us this, well, practically not so much possible, but let's try, as we just mentioned, 54 and then minus 54 and 54 and minus 54. Now we like to repeat until the psi-U failure index equal 1. And let's say this is only what? Only 1 millimeter. Okay, 1 millimeter. Let's take a look at the psi-U. Is what? 60. 60. 60. What does it mean? psi-U. 60 means that we have a very high stress. So 60. So let's say approximately. Okay, approximately. Let's say 60 times. And this will give us the about stress of psi-U index is equal 1, right? So under this much radius or diameter and this much pressure, and the total thickness has to be 60 millimeter. Okay, 60 millimeter. That is the what we need to understand that, and this one is based on psi-U or failure criterion. Okay, so for this much pressure vessel to design and plus minus 54 degree, and the thickness has to be 60 millimeter. to reach the, that's what the SIU failure index telling us. Okay. And Psi Hill and the sigma max failure criterion and so on. Okay, well, let's have a 10-minute break, and then let's continue to other task. Okay, see you soon. Okay, let's get back to class. One more topic I'd like to clarify again is the permeability. Last time we briefly introduced the how to use this tool to better understand the permeation or infusion process of the infusion through a laminate. So as you can see in this tool, we have two main worksheet. One is the main CLT, which we used for the so we have two main worksheet in this high CLT. One is a main CLT where we specify all the layup sequence and loading condition, and then output will be the strength ratio and so on. Now, another one is the main permeability. There is another worksheet, and all the layup sequence will be given in this worksheet, but in main permeability is an additional worksheet which we can use to better understand the permeation in the laminate. Okay, well, I will skip the detail the theoretical background, but you can find there is another help file in this worksheet, and also in your lecture notes. I just like to give you an idea how to use that. The purpose of this main permeability is to draw to understand how fast the resin can flow in two-dimensional flow. Say at the center, we have a resin source input, and then we have a certain laminate, and the resin will flow for every direction. Since all the boundary, we have a pressure zero, vacuum, and the resin source will be the center. So depending on the laminate sequence, the resin will differently flow, and making this kind of elliptic depending on the layup sequence. This is the pictures, as you can see that. As you can see, resin will go in at the center, and the resin will flow. Again, all the boundary, we have a vacuum, and also we have many layup sequence. This is a very typical, very useful methodology to measure permeability of this laminate in two directions. Just one test, we can measure the two directional permeability, K1 and K2. And also K12. So let us so in here you starting from again similar to stress analysis, use start with a select material number and also a layup sequence and also a thickness. Well, thickness, let's get back to a 0.125 regular one. And then we chose number 4. What does it mean? Number 4 means that we chose the T700. And then important material property here is the on-axis of permeations. Usually the order is the 10 to the minus 10. So here KXX is a uniaxial on-axis. KXX is the 0.195 and in the Y direction 0.025. This is the order of the permeability. And notice that this is the 2 and Z direction. We don't need a Z direction flow much, but the Y direction in transfer to a fiber, you can have a very slow, almost the just the 10% slow, 10 times slower than one direction. I need to change this value to others as well. So this is a very typical, can be a typical value. So please remember that one fiber direction is a flow faster than transverse direction, about 10 times. Okay, so this is the material property, and this is the what we know. What this can be back calculated from this analysis. So here we chose the material number 4 and the layup sequence and certain laminate. Again, let's do 0, 90, and then plus minus 45. Okay. And we did this simulation last time, but last time I just want to make sure again. And how can we use this this quick chart to get the this kind of I mean the flow patterns? And for your understanding, I just made the sample of the quick chart. You just copy here. Then as you can see, input value still is an input, and then x length, y length, and then k, and what does it means? X length is the equal x length. X length is the defined here, x length, and then y length. All the theory is there. So x length means that it flows after this much time, 120 at the time. What will be the x length and y length? So for given angle. So okay, what it means is that you have a certain layup sequence, whatever layup sequence you have, and then the resin will flow from at the center, and then it flow goes like that. Okay, this is the x, and this is a y. So after say 150 seconds, and then we will have a flow in x direction and y direction. So and alpha, what does it mean? We similar to drawing the failure envelope, we like to draw all the envelope, the flow, we call a flow front line. So we for the every angle, we find this point, that point, that point, we all the line, and then we try to make the circle. So that is the x length and y length. And then kx and ky is the similar to this. We have in certain direction, we have a kx and ky. and Kx and Ky. That's a permeability in that direction. So that is the output. So again, I will skip the theory. You can find it from the references I mentioned in this slide. So well, actually, that's all you need to understand. And this one is the there is a nonlinear equation. We have to find the one makes it 0 here, which is a zeta. I recently upgraded the program so that this zeta, which makes the formula is 0, is automatically calculate. Find the 0, find the zeta, so that formula equals 0. Sorry, I didn't fully explain the meaning of the zeta, but just to understand, this zeta has to be chosen to make this formula equal 0. So again, this a very simple form. The formula was entered here, so it can automatically make. So solve this nonlinear equation. So all you need to do is just change this time, and then this angle will be chosen by the input. Input is the one we're gonna use this input. Okay. So permeability. Let's say we have a choose a 4. And then what we like to do is the plot those envelope by changing these all the angles and the permeability and this one. Okay, so let's do that. Okay, this is the plot we just got using the layup sequence and using this permeability worksheet. And what we like to do is the plot this this one, and then let's try to draw. Again, let's try to make the scale. I don't know what is this point. Okay, so this is the floor line. Again, the make sure this dimension is scaled so that x-axis and y-axis are same ratio, is makes it scale. Okay, so I'm gonna copy to here, and we have a section on the permeability, which I think we have a process simulations. We have a section for, yeah, let's use that one. Okay, well, this is the again, to get this value, we have to make sure the permeability. So time is the 120. Okay, so 120. What does it mean? Okay, first of all, layup sequence is the 0 plus minus 45 quasi-isotropic, and then at time equal 120 sec, this this will resin flow, and then at time equal 120, we reach this one. Now is very interesting. Why is it precisely circle? Well, This is the 0, 90 plus or minus 45 and symmetric. As you can see, is a quasi-isotropic. So quasi-isotropic means the structurally is a behavior like the isotropic, but flow line is also isotropic. So everywhere, resin flow in every direction is the same amount. Okay, this is a very interesting to know. And now let's try to change the value. Say, what if we have a different time? Different time means that, let's say, 240 sec. Again, this one is automatically chosen. And then let's try to draw, let's say, with another one. And then plot them. And here, of course, very similar. I'm sure they're similar plot, but the difference will be where are we? I'm gonna plot over here. I'm sorry, I need to. No, not this one. Oh, well, there was a previous point. That's why we had a. I need to delete this. Okay, I'm gonna. Fine. Okay. So here we. Okay, this is the plot we just calculated. And also this is a circle. I'm gonna delete this. This is the circle. And also this is the one we plot before. And this is the one. Okay. And then I'm gonna plot like that. So what does it mean? It means that, okay, this one, the blue line was the time equal 120, and this one was the time equal 240, which we just enter here. As you can see, we enter the 240. So what gives us, it gives us is that the flow line after a certain time, as you can see, this can be very useful to predict how this circle. Again, this flow source is here, then the resin will flow every directions. And while this can be used to back calculate permeability of each ply, each XX, KXS, KYU, and so on. And here it predicts the flow line with a given permeability, but using this output, you can back calculate the on-axis permeability. Let's say you measure you measure them and you can back calculate it. But anyhow, this is very useful. Let's do it one more time. Let's say we change the 360. Then I just want to make sure this is the right one. Okay. And then here we change it to the output as a 6. And then a quick chart. So every 120 and 240 and 360, and then you can see that this the circles, flow line will change like that. So we can plot over here. And as you can see that we flow more. So we can plot here. Okay, so the, oops. So the 120 and 240, and the third one was 360. So as time goes by, you can predict, or you can measure this, and then you can back calculate the K11, KXX, and KYY, and so on. Okay, so let's say we don't need this. I'm gonna delete this one, and now let's imagine what will happen to if we have a biaxial laminate, what will be the flow line? That will be a interesting result. Let's take a look at. Let's say we simply change the layup sequence. Layup sequence like the simply 45 and say minus 45. Okay, and 45 and minus 45. And this biaxial 45, or let's say with a more clear, let's try to 60. Okay, plus minus 60 biaxial, and then show the what will be the flow line. And with this, and at this point, okay, we'll double check, we automatically find it. Okay, and then this one, okay, time, let's say, let's fix the time, and then the change this in file, and then well, right now we just keep changing the parameter and get the result and plot. That's all what we do. But very importantly, by observing this behavior, we better understand the behavior of the structurally, and also I'm trying to make the this one is a scale, because You know what I'm saying? This is the make sure this is a scale so that we can have a real dimensional flow. Okay. So this is the what okay will be better just plot this one into here. Okay, I don't want to mix up, and I just want to plot these things into here, and then you can see, aha. So biaxial laminate, you would have a different flow line. Of course, more toward the y direction because this is a plus minus 60. As you can see, we have a more flow line because the fiber direction, we have a more flow speed, more permeability. So as you can see, so as you can see, physically it makes sense. So this is the just plus minus 60, or you can say 60 symmetry, and then this will be the and this one at the same time equal 360, but the bottom one is the quasi-isotropic. This is the BX60. So as you can see, we have a more flow speed in y direction in BX60, simply because the fiber in fiber direction we have a more resin flow. So this is a very interesting observations, very quick and very useful observation of the understanding infusion process. Okay, so now you can imagine how much the parametric study you can do. Okay, so of course I'm going to share this PowerPoint. I mean the lecture note today's. Hmm? Okay, I'm gonna save it. I'm gonna share with you after class. Now, I like to go quickly more advanced topic of permeability. Uh, well, this micromechanics can be applied to understanding or calculation of a structural behavior, but also the micro multi-scale approach can be also applied to this resin flow. Let's say the tow and fiber will have a certain level of the resin flow, so we can start study about this all the fiber, tow, and I'm sorry, this slide is a little bit not well organized, but my point is that we can have a 090 micro multi-scale analysis of permeations, and so we can predict not just the by the measurement. Sorry, I just copy in here and then some. So I just want to give you an idea that give you the micro mechanics or a multi-scale approach can be applied to understanding of permeations. Okay, so uh, hmm. And very interestingly, this can be, as you can see that, this is the permeation streamline of NCF. NCF will have a certain stitching and certain direction. And this also can be well, this is the fluid mechanics using this. So permeation is not just measured, but calculated using the flow analysis, using the fluid mechanics. So I just want to give you an idea that this multi-scale approach can be also applied to understanding of the infusion analysis. And well, okay, so sorry, this. So we can not just through, we don't need to measure, we just do a micromechanics analysis to calculate all kinds of permeability study. This is a really useful and the academically very useful study. Now, this permeability is the same thing. RTM or just the infusion is physically pretty much the same. RTM versus infusion is the only difference will be the mold, closed mold or open mold. That's the basically a difference. Sorry, I just want to give you the most important point I like to emphasize is the when we make the RTM process. Sorry, this all the RTM process applied to automotive part. RTM simulations. Okay. This is the first we need to have a draping. A draping means that we have a flat fabrics, just a dry fabrics. We need to have some pre shaped, and we can measure the all kinds of this is just a dry fabric, okay, to simulate all the drapeability. How can the fabric shape, and then we have a to make this automotive cabin part, the CFRP cabin, left hand side, driving side or passenger side. You have a B pillar, A pillar, and C pillar with a roof, and this whole body is made by piece by piece like this. Okay, and then put them together and make one structures. We assemble 10 parts, and then this is all dry fabric. And next step is the of course this is structural analysis, but next step is that we do a draping. Draping means this is the fabric, just the make the shape and to put over the mold. Okay, this is no resin, just a draping, the shape. And this draping analysis is important because all the layup sequence will give us the final layup angles. Is very difficult to simulate or understand the final layups without this draping. So draping analysis will give us the final shape or final angles. So each 10 part will have we can do this draping simulation, and then we can have all the draping analysis, and then we can, here is the inlet and outlet. You can see that resin, how can resin will flow, and is through this simulation we can understand where the resin should be in or where the resin should be out. So we can design resin inlet and resin outlet. So this is through permeation analysis, which we just did. We just did it. So this is a resin flow simulation using all the permeability. So we can analyze using the very important tools. It's called PAM composite. Speaking of this draping, okay, this is one of the draping. I'm sure you saw this one before. But let's say we have a flat laminate or a woven, and then this is the just please understand what it means by the draping. This is a draping analysis. Okay, just the how this fabric, dry fabric, or thermal forming. You can imagine there's a resin there, but you understand how this dry fabric will deform. This is an experiment, and then depending on all the layup or open fabrics that we can do this kind of simulation. And so depending on the plane or setting or tool, the final form will be the different, and the load pressing, and we have a die. We have a die and press. You can see that what we can do. Okay, and then we can also simulate the curing process. So once we have a draping and then RTM, and then we can cure that, and we can have predict the residual stress. So I will not cover all of this study, but it's important to understand what you can do in the real simulations. So PAM composite is starting from a PAM form and PAM RTM and PAM distortion. So PAM form is like the draping, just a shape with the dry fabric, and PAM RTM or infusion is that resin will flow, and then curing, you will have a cured structures distortion, and there will be a finally you can observe what the shape will be. So understanding of this process simulations is a very critical. You can do this all the process using the PAM composite, which is very useful to simulate the behavior of the manufacturing process of composites. Well, it can be applied to many different PAM RTM and PAM form. Okay, again, PAM form means that you just shape the dry fabric certain shape, and then RTM let the resin flow, and PAM distortion is they let the composite cure, and then you can see how this resin, I mean the composite can distort after curing. So understanding this three step it can be very useful. Sorry, I have a duplicated. So this is the one. See, this is the draping, but it can be also applied to a PCM. PCM means the pre-preg compression molding. So you have a wet resin, and then we press, and we can. And oops. Okay. Now, as you can see here, how can we deform various shape? Imagine you make the battery pack and then using the some sort of pre-preg and then press and then you can predict the final shape. And this, by the way, this is not simulate through PEM. This is a simulate using abacus. And then how do we do that? Well, imagine that each toe and the toe, so much toe, we model that. And then between the toes, we can introduce a sort of frictions, coefficient. Uh, uh, so we have so much physics in there. So at the corner, and you can see that how this corner shape will change, different from other positions. So let's say you make the this kind of a box or battery pack, and imagine that don't assume that all the layup sequence will be the same as the original one. You know, once you press that and the shape changes, all the layup sequence angle is changing, and there will be a more resin rich area. So resin fiber volume fraction will be lower. So uh, I don't mean to how to calculate to discuss how to calculate, but the understanding this kind of behavior is a very important in design or manufacturing of the composites. Okay. Well, I'm trying to cover as many topics as possible. So that's the idea of the all the composite manufacturings. Composite manufacturing, the most important point is we have a dry hose or fabric, and we have a resin. How can we implement or impregnate resin into a composite? That's it. And the resin will be cured. If that is a thermoplastic, then it will be a heat and press. The composite will be cured. And if there's a thermoplastic, then there will be some chemical reaction. So simply like that. Well, it's not simple, but that's a basic idea. And I add a session of the comparison of the thermoset and thermoplastic, which is a very critical issue these days. Well, thermoset is the very common and still widely used, but the thermoplastic resin or thermoplastic composite will be uh, uh, the goal we like to reach or achieve. So there can be many different thermoplastic and thermoset. Uh, this is the good uh, figure explaining thermoplastic, the PEC or PEEK or PVDF and PA11 and acrylic and PA6 and PP. The top to bottom, you can see the level of the thermoplastic. So PA6 is a low level, and acrylic is a little bit above, and PA11 and the PEC is the most strong uh, thermoplastic. Okay, so the summer set process is the always the oh man, we always need to apply the temperature and pressure, and so thermal set I'd like to emphasize that, either thermoset and thermoplastic for chemical reaction, we always need a pressure and temperature. So thermoset, the pressure doesn't need to be high, it's very low pressure. And temperature, we have a certain level and very long time. See, always a three: pressure, time versus, pressure, temperature versus time. So thermoset, like epoxy, pressure can be low and temperature is not high, but very long time. Why? Because we need a time. We need to wait until all the chemical reaction so that all the polymer can cross-linked together. That's the thermoset. Now, thermoplastic is that we need a very high pressure, high temperature, but very short time. That is the characteristic of the thermoplastic process. So this is like a entangle of the polymer chains. So we don't have to wait, but we need to apply a lot of pressure and a very high temperature to entangle them. So mix them, all the polymer chains. Okay. So if we do a stress strain curve, this is a very typical thermoset and thermoplastic. Thermoset is very much brittle and cross-linked, and thermoplastic is the in general we have a lower strength, but we have a very large failure strength. Well, not always, but this is a typical behavior. Okay, so if we have a 090, we have a thermoplastic and thermoset, we could imagine that a different behavior. So let's say extreme case is a 0 and 90 under certain load case. Okay, this can be important in understanding of a composite. So I'm gonna explain this one. Okay, let's imagine 090. We apply this certain strain because the composite always behave together. So strain. Now the transverse direction, the resin side, because of a high stress concentration, and there can be easily cracked between the fiber and resin in UDT. Now, because of uniform strain, the UDL and UDT has to have deformed in the same strain. So UDT may generate more cracks in the UDT. So the again, UDT, there's not supposed to take load, but it's better to have a high failure strain in the UDT. Okay, so that's why the thermoplastic can be better, because UDT we have a higher failure strain due to a resin system. So that is one thing we need to notice. You need to know. And then if we have a biaxial load like that, this thermoset case, this load will cause a crack in the 90, and this guy will cause in the 0 degree. So biaxial case, this could happen in thermoset, but the thermoplastic is that this guy, while the resin will have a much higher failure strength, there's not much crack, and this one is the same thing. So I just exaggerated the situation, but the higher failure strength of resin is very critical in composite. That's what I like to emphasize, that as a result, even though the thermoplastic resin has a lower strength, but higher failure strength means that the thermoplastic laminate as a result can be higher strength than thermoset laminate. Why? Because as demonstrated here, the even fiber directional load or strain may cause the crack in the 90 degree. So that this may cause the initiation of the failure and so on. So point is that the higher failure strength is the pretty much important. Thermoplastic in general has a higher failure strength. I mean the resin. So that can be a very beneficial in composites, and even good for the impact and so on. Okay, that's I like to emphasize. So two things: thermoplastic, where manufacturing process can be different, quite different, two different characteristics, and the structural behavior wise, the thermoplastic, the high failure strength is very beneficial in composite, and of course the thermoplastic is a recyclable. That is the very important in these days. So but conventionally, all the way, thermoplastic has is a little bit lower strength like this. So they prefer to use the thermoset. But nowadays, the thermoplastic, the technology has improved a lot, and we have a PA11 and PA many polyamide systems and PEC and PPS. PPS is about here. PP is very low. PP is known as the lowest, and PA6 and acrylic PA11, and PPS is about here. Okay, it's good to remember this of triangular. Okay, so I try to cover the resin, manufacturing process, simulations, and the thermoset and thermoplastics, and also importantly, failure envelope. Okay, so that's the what I like to emphasize, and so using our tools, of course, this tool. The high CLT is based on the old theory, and we just the program based on the older theory. Now you can use this tool to design, and most importantly, you can use these tools to better understand the composite behavior, structurally or manufacturing wise. Okay, so this can be very important. Now there is one slide, the worksheet. Let's say we have a composite plate, and then a buckling behavior is I cannot emphasize how important it is. Buckling, most of the structure it fails under buckling, not just the under tension. Except the pressure vessel, that the buckling is the most important structural behavior. So in buckling, it has the of course the most all the structure has the certain behavior of buckling, and buckling has involved a lot of buckling mode. You need to understand buckling mode and buckling load. What is a buckling mode and buckling load? Well, each buckling under certain load, the structure will buckle. But the buckling always associated with a certain buckling mode, shape. I just want to. So buckling is the a little bit advanced topic. Okay, this can be a very important problem statement, but here we don't have a slide about the buckling here. But since we have a worksheet, I like to very briefly introduce about the buckling. Okay, this is the structure buckle. Well, there could be a lot of story and theory involved in this buckling, but let's say we have a plate, and then we have a certain boundary condition. Okay, boundary condition. Let's say all simply support. Okay, simply support, and then we compressed. Now we can have this will certainly buckle. Okay, this will certainly buckle like this. You can easily imagine, oh, this will buckle like that, but not always. Depending on the A and B ratio, it may buckle easily like that. It's more difficult to buckle like that. So buckling mode load can be lowest buckling load will be the practical one. The point is that this may buckle in real world, not this one, not that one. Well, this is not always a story, but the buckling mode and buckling load is depending on the length ratio. So this is the P critical, and this mode will depend on the A and B. So I just want to, I don't mean to give you a full lecture on the buckling, but say give you some, very basic idea about the buckling. So NX and NY, the shear load may cause another buckling as well. And so this is the length L1 and L2. And then the load we apply, PY and PX ratio, and the shear load ratio. And then this is the one, the layup sequence will give us a certain bending stiffness, bending. So this one is the from our laminate sequence. So this is comes from D11, D12, D22 is the bending stiffness, which comes from our here, as you can see, this is a bending stiffness. So D11 and D12, and you can see that this is a bending related property. So that would be determined by the older layup sequence. So once we have a layup sequence, this D is a critical one. This will be calculated automatically from this worksheet. And then, as you can see, this all number in red will be the output. From so this one is a theoretical result. We can see that all the critical load, and then mode, J mode and I mode, what does it mean? This is also important. Depending on this length ratio, the I mode is the mode shape I just mentioned, like this, will be determined. So let's say we have a 4 meter and 4, and then the 4 and 4, that mode will be a 2-to-1 ratio. Why 2-to-1? Why buckle like that? Well, is again depending on the layup sequence. very interestingly, we have a plus minus 60. In this case, and the length will be a 4 to 4, then buckle will be a 2 to 1. 2 to 1 is the exactly like that. It's a 2 tons, and then this way is a 1 ton, one shape, one the concave, convex, and two up and down, and this. That's the what the I mode and J mode, and then this is the load. So all the theory is comes from here. You can find the more information from the references, but the idea is that all the buckling load, this is the buckling load, is the one you can calculate for the given laminate and then a given dimension. And this is very important. Let's say this is all the 0, 90, and 45 and minus 45. This is exactly quasi-isotropic. And then let's say this is the okay, this has to be slightly is not for the isotropic. So that's why we have a little bit of a error there. I would say sorry, I need to double check this one. But I need to see why this is the divide by 0 Lx. Well, I used to use this equation, but I don't know why this makes this was the main causes. Don't get the reason, but I don't mean to discuss about the precise number, but the point is that this depending on the layup sequence, this is exactly X and Y plus minus 45, and then we have a ratio of 4 to 4. Then this mode is 1 1, and this one will give us the some buckling load. Okay, so this one, let's say 1 to I don't understand. Okay, well, I don't mean to cover everything, but I just want to give you an idea that this bending stiffness calculate can be from this one, and then using this one, you can understand this. Just give me 1 minute. Why this is become 0? LX I0 I0 1 makes the divide by LX divide by the LX LY Y. I don't understand why there's a divide by 0. Okay. The more reason is this guy.
Professor, the I0 is a zero cause the problem.
Yes, I mod
Yeah, I0 equals zero cause the problem is the function doesn't get the result.
PX pure I, PX pure I1, I0, and I1. So the YI0, I0 plus 1. Okay, so x11 and then okay. We take the integer here. Integer makes the mode. If this is the well, it was a little bit long time ago, but if this is 0, then it has to be 1.
Professor, in the function, if the LS is
I don't
less than
understand.
L,
Okay.
yeah.
Do you know how to program that? Okay, so this is the one. You have a I0 has to be 1. None. It has to be a 1. But it has the 0 because we want to change it to an integer depending on the theory. That caused the problem. So the it has a pressure, compression, and shear, and pure compression and pure shear. We have a different equations. Now this is my point is that the I mode 1 and 2 has to be related. Mode shape is related to a mode critical load. That's why in calculation of the buckling load is critical. Okay, I need to double check here. It's been a long time to program this one, but anyhow, the point is that you can A very important point is this one. This one can be from the our composite laminate bending stiffness. Once we have this, all you need to do is just the enter here. As you can see here, you need a D11, D12, D16, and all of the buckling load. You need a D, right? All you need is the D. That's my point. D will be calculated from all the layup sequence. Okay, layup sequence, and that is the D. Okay, since this buckling worksheet is there, that's the I just want to emphasize that this high CLT can be used to calculate the buckling load. Okay, and it is the it can be used for the for other applications. Such as the optimization. It has optimization tools which can be very usefully used together with this one. Well, right now we use the quick chart and quick chart 2 to vary one variable to show the result. But using the optimization, you can plot or get the results more effectively to get the results. Okay, what else can I like to emphasize? Okay, well, these tools will be used. Now we are ending the end of this semester. Of course, all the homework and the term project will be related to with this high CLT, how to use that. So please try to learn this one. Again, this can be very useful for your future study. And okay, so we are preparing for the the end of a semester. Okay, so this is what we like to cover today. And next week, we will have we will not have a class. And then we will have, I will announce one more for class, but not next Wednesday. I will let you know. And then together with, I will announce the homework, and then soon I will assign again the Tom project as well. Okay, so mostly you need to use these tools and the understanding all the composites. Okay, that's all I like to cover today. Is there any questions? Okay, well, Thank you so much, and then keep in touch through Talk.